Imagine tapping into the ultimate cosmic powerhouse, a black hole. Sounds wild, right? Well, it's not just crazy talk. Scientists say it could be an incredibly efficient energy source. Now, you might think the black hole itself is the key to unlocking this power, but hold on, that's not exactly how it works. The genius of Stephen Hawking revealed that black holes do emit a tiny bit of radiation from their event horizon. But don't get your hopes up, it's not enough to fuel anything substantial. What really gets things buzzing is when matter meets the black hole. Most black holes are spinning like tops, and this intense rotation creates an area called the accretion disk as material gets pulled towards them. Now let's get real about what happens when matter meets a black hole. As it spirals inward at mind-boggling speeds, this material starts heating up like crazy due to friction against itself. Yes, imagine getting a cosmic rug burn. Scientists have observed this phenomenon mainly with gas from stars, but the laws of physics say it should work the same way no matter what you throw in. All that friction generates heat, which then converts into radiation, primarily X-rays emitted perpendicular to the disk. This process is so powerful that much of the falling material gets completely vaporized before reaching the black hole. Here's how extreme this black hole snack attack is. A massive chunk of what it ingests transforms instantly into light, radiating outward in an electrifying display of energy. This process isn't just intense, it's also really efficient. The X-rays and other forms of radiation produced are so potent that they outshine any light emitted by the black hole itself. For context, our current best nuclear power plants can only convert a minuscule of 0.1% of uranium-235's mass into energy, whereas a black hole takes the cake with its jaw-dropping matter-to-energy conversion rates. Let's take a look at just how crazy efficient black holes can be while our sun manages to convert around 0.7% of its hydrogen into energy, leaving us with helium as the byproduct. A Kryton disk in a black hole can achieve an astonishing matter-to-energy conversion rate of up to 40%. To put this into perspective, if we were able to harness just 1 kilogram, that's roughly 2 pounds, of matter at this level, it'd yield an incredible 36 petajoules or 10 terawatt-hours. That's enough energy to power our entire world for half an hour. A metric ton could keep things running for 3 whole weeks. The potential is truly mind-blowing, and the only missing piece is figuring out how we can tap into this extraordinary phenomenon. You're about to discover a groundbreaking concept in astrophysics known as the Penrose process, proposed by none other than Nobel laureate Roger Penrose. This extraordinary mechanism enables us to extract energy from a rotating black hole. Now, here's where it gets really fascinating. Instead of relying on energy within the event horizon, this process taps into the rotational energy that exists just outside in the ergosphere, an area of curved spacetime, where any object moving through it is essentially pulled along by the rotating space itself. Picture a lump of matter entering this ergosphere and then splitting into 2 distinct parts, propelled apart either by powerful explosions or advanced propulsion systems. The key lies in timing their separation so that one piece successfully escapes the black hole's clutches while the other remains behind. The Penrose process, an incredible way to tap into a spinning black hole's hidden power. Here's how it works in a nutshell. Imagine matter falling into this cosmic whirlpool. As it approaches the event horizon, it enters the ergosphere, a region around a rotating black hole where space itself is curved and gravity gets twisted. The key to unlocking energy lies in splitting this chunk of matter right at the edge of the ergosphere. With perfect timing, one piece zooms out to infinity while the other falls towards oblivion within the event horizon. Now, here's the mind-boggling part. With meticulous planning, the escaping bit can have more energy than its original form, and the infalling piece carries negative mass energy. Momentum remains intact, but this process essentially borrows additional energy from the black hole itself. Since we know that rotating black holes exist out there in our universe, following the principles of relativity and astrophysics, we might just unlock new secrets by studying this phenomenon. Let's dive into the formation and unique characteristics of these cosmic powerhouses, black holes. Imagine a star collapsing under its own crushing weight, unable to resist the relentless pull of gravity. As it compresses, normal space-time breaks down, leaving behind an abyss so dense that not even light can escape. Given stars spin due to the law of conservation of angular momentum, their black hole counterparts must also rotate with considerable force. Roger Penrose revolutionized our understanding by proposing a groundbreaking theory. Energy could be extracted from these cosmic whirlpools themselves. Now envision a spacecraft hurtling towards a spinning black hole in harmony with its rotation. As observed from far away, this spacecraft wouldn't just maintain speed, but actually gain an impressive boost as it approaches the event horizon, a point of no return where anything, including energy, is swallowed by the void forever. Imagine a space mission where you not only survive but also harness the power of a black hole, turning it into an ultimate cosmic accelerator. If a spacecraft is cleverly fueled and its engines are fired in sync with the black hole's spin, it can essentially perform a supercharged gravitational slingshot. This allows it to escape from the vicinity of the black hole, significantly accelerated. But how does this work? The key lies in the concept of frame dragging, an effect predicted by Einstein's theory of general relativity, where a rotating black hole drags space-time around with it as it spins. As our spacecraft enters and then exits this cosmic whirlpool, it can gain energy from the rotation of the black hole itself. This means that not only does the spacecraft escape unscathed, but it also carries away some of the black hole's rotational energy. This transfer of energy results in a noticeable decrease in the black hole's spin as it adjusts to account for the inertia added by our brave space explorers and any fuel they may have left behind, an incredible display of how our universe's laws can be used to defy gravity itself. Thanks for correcting that. Let's rewrite the script with the added knowledge of the Penrose process. Imagine a space mission where you not only survive but also harness the power of a black hole, turning it into an ultimate cosmic accelerator through the infamous Penrose process. If a spacecraft is cleverly fueled and its engines are fired in sync with the black hole's spin, it can essentially perform a supercharged gravitational slingshot. This allows it to escape from the vicinity of the black hole, significantly accelerated. But how does this work? The key lies in the concept of frame dragging, an effect predicted by Einstein's theory of general relativity, where a rotating black hole drags space-time around with it as it spins. As our spacecraft enters and then exits this cosmic whirlpool, it can gain energy from the rotation of the black hole itself. This is possible thanks to the Penrose process, which describes how an object can split into two parts. One falls into the black hole, while the other escapes with some of its rotational energy. This transfer of energy results in a noticeable decrease in the black hole's spin as it adjusts to account for the inertia added by our brave space explorers and any fuel they may have left behind, an incredible display of how our universe's laws can be used to defy gravity itself.